Hello, everybody, and welcome to Chapter 16 in Dynamics. This is Professor Algara with another lecture video to explain you a little bit more about, kinematics and kinetics. This chapter particularly will be divided into two different videos. So today we'll be talking about angular position, angular velocity, and angular acceleration and how they relate to everything that we have learned until now. Then next week I will post the last part of this chapter. All right. Let's just get started. And at first, we're going to be talking about rigid body motion. So in the past, through the chapters that we already studied, we've been talking about particles and how these particles move through a path. And then we have studied equations that will help us dictate, everything related with that movement. There are some cases where an object cannot be treated as a particle. In these cases, the size or shape of the body must be considered. Rotation of the body about its center of mass requires a different approach. For example, in the design of gears, cams, and links in machinery or mechanism, rotation of the body is an important aspect of the analysis of motion. We will now start to study rigid body motion, and the analysis will be limited to planar motion. So when we're talking about planar motion, right, we're looking at a plane that will dictate the motion of the rigid body. So, and we will divide that into three different type of motion. So at first we have a path that has rectilinear or curvilinear translation. That's the first one we'll be study, and then we will move rapidly to a rotation about a fixed axis, and then what is called a general plane motion, which combine rotation and translation at the same time. Translation occurs if every line segment on the body remains parallel to its original direction during the motion. When all points move along straight lines, the motion is called rectilinear translation. When the path of motions are curved lines, the motion is called curvilinear translation. Rotation about a fixed axis. In this case, all the particles of the body except those on an axis of rotation move along circular path in planes perpendicular to the axis of rotation. So basically, you're studying a body that is rotating around an axis and you're looking at each one of the particles within your object so you can study the motion. And general plane motion. In this case, the body undergoes both translation and rotation. Translation occurs within a plane and rotation occurs about an axis perpendicular to this plane. An example of bodies undergoing the three type of motion is shown on the mechanism that you can see here. The wheel and crank will undergo rotation about a fixed axis, as you can see here. In this case, both axes of rotation are at the location of the pins and perpendicular to the plane of the figure. The piston undergoes rectilinear translation since it is constrained to slide in a straight line. The connecting rod undergoes curvilinear translation since it will remain horizontal as it moves along a circular path. And then the other connecting rod will go into a general plane motion since it will, both translate and rotate at the same time. Let's just remember a little bit what we have learned before. We have, a translating part or a translating body, and you have points A and B. So in order for you to study how they relate to one another, you have to have a fixed coordinate system, as you can see here, so you can establish the position vector from this origin all the way to each one of these positions. And if you have that in place, you can easily build up an equation in order to find the relative position from B to A, right? So as you can see, and you remember that from before, position of B is equals to position of A plus the relative position from B to A. Once you have that and you have your equation built up, you can derive that equation respect to the time in order to find your velocity and acceleration. Okay, and once you have that, you just have to remember that all of the points within that rigid body, they will move along with the same velocity and acceleration. When a body rotates about a fixed axis, any point in the body travels along a circular path. The angular position of P is defined by theta, as you can see here, right? So the change in angular position d theta is called angular displacement with units of either radians or revolutions, and they're related as 1 revolution will be equals to 2 pi radians. So this is something that you need to save because it'll be very helpful for you to convert from revolutions to radians. So once you have that equation of d theta, you will be able to derive that equation respect to the time in order to find angular velocity, or omega, as we call it, because of the Greek letter. So then you can also, after that, derive that respect to the time in order to find angular acceleration. So these equations are very similar to the ones that we already studied, in previous chapters. If the angular acceleration of the body is constant, the equations of angular velocity and acceleration can be integrated to yield to a set of algebraic equations that are just given by you. So when you have this particular one, you can just directly use these equations that will help you get the answers that you're looking for. And this one relates, just exactly the same way with the equations that we already know for position, velocity, and acceleration. When acceleration is constant, then we will have something similar to this. You remember, you know, velocity at the end, it's equals to initial velocity plus acceleration or constant acceleration times to the time, and you can do the same thing for 2 and 3. Theta 0 and W 0 or omega 0 are the initial values of the body angular position and angular velocity. Note these equations are very similar to the constant acceleration relations developed for rectilinear motion of a particle. The magnitude of the velocity of p is equals to angular velocity times the radius. The velocity's direction is tangent to the circular path. If the vector in the vector formulation, the magnitude and direction of v can be determined by performing the cross product of angular velocity and rp, where rp is a vector from any point on the axis of rotation to the point in which you're starting. An equation that relates them both will be velocity is equals to angular velocity times that radius. And the direction of v is determined by performing the right-hand rule. Just going back a little bit into statics. So using the vector formulation, we can just, change these equations or work these equations as the time derivative of the velocity with respect to the time. That way we can reduce the equation to this by performing cross products of these different vectors, and the equation will reduce to this, keeping in mind that the acceleration or the magnitude of the acceleration can be obtained by taking each one of the components to the square and the square root of all of that. All right, let's just study what we just learned. So we have a rigid body, and this is the center of rotation. We're studying how this P move from P prime, right? It's not giving us a P prime, but anyways, it's just the location of P after T equals something. So the distance from this center to P is what we call R. And then the distance from here to here is also R. We are studying how these particles move from this point to that point, and we're going to call that d theta. For us, then, will be easier to find the S, which is what we're studying here, how it moves. Right, since we're looking at an equation that relates position with angular position, it's given by the book as ds is equals to d theta that multiplies r, right? If we derive both equations or both sides of the equation with respect to time, we get that ds over dt, it's the velocity, right? That's from before. And this term will become now something that is called omega. And this multiplies the radius. Omega is the angular velocity, and this is the regular velocity that we're so used to calculate from before. With this equation, we have relate, you know, displacement or position with angular displacement or angular position. And then we have also related this with velocity and angular velocity. Okay, so far so good. That's for velocity. When it comes to acceleration, right? Acceleration. We know that acceleration by definition will have a tangential component and a normal component. And from before, we know that the tangential component, it's got it as we derive speed respect to time. And then we know that the normal component, it's equals to velocity to the square that is divided by rho. Okay? And rho is the radius or the radius measured from the center to the location of P. All right, if we know that, all we have to do to get the first one is derive dv respect to time. So if we derive this equation respect to time, we will get that the tangential component is just not more as a new term that is alpha that multiplies the radius, where alpha it's what we call angular acceleration. When it comes to this one, all we have to do is to plug this value of velocity into the equation. So the normal it's equals to w, or angular velocity that multiplies the radius, this to the square, over r. This will be wr square over r. One will cancel with the other one. Then we get that this is equals to w square times r. And these guys are just the terms that were introduced to you in the previous slide. So I really wanted to get that for you so you can know where everything comes from. And we know also that if we want to know the magnitude of that acceleration, it's just equals to the components to the square root of that, and that will give us the magnitude of that vector. You can also get that, as I said before, from just performing the cross product of the vectors when they're given in the vectorial form. All right. All right, we need to establish a sign convention along the axis of rotation. If a relationship is known between any of the two variables, then we can use the equations that we had learned before. As you know, angular velocity is, the time derivative of the angular position, and so on and so forth. We can utilize those equations. If alpha is constant, alpha is angular acceleration, then we will be able to use the equations that were given before. We can also have the following equations in order to find the scalar forms, of these values. And then if you're given with a vector form, then you can use the cross product of these equations that are as given right here. All right, let's just put that into numbers. So as we see this particular exercise, it has a combination between linear motion and the angular motion that we have just studied. But the motor turns gear A, as you can see here, with a constant angular acceleration of 4.5 radians per second square starting from rest. The core is wrapped around a pulley right here, D, which is rigidly attached to gear B. We need to find the velocity of C and the distance it travels in 3 seconds. So we need to find, the velocity and how much it moved from here to this point maybe. Okay. So if that's the case, the best way to approach this exercise. So if we put that into numbers, we know that what is given is alpha A, which is 4.5 radians per second square. They told us that it comes from 0. They're telling us that we need to calculate VC and also the position at t equals 3 seconds. And we were given with radiuses and everything. Okay, so if this engine is moving with an constant angular acceleration, they're telling you that this guy also moves with a constant acceleration, because this one will move the gear and the gear will move the pulley and the pulley will move number C. So we have to study the movement in the different parts of this exercise and start assuming things, right? So since the motor move with an angular acceleration, it's very easy for me to say the acceleration of C is also constant. And because it's constant, then I can use the equations that were given to me. What is very important here is that you know exactly what you have and what you need. Since the acceleration is constant, like we said, across everything, we will know that we will know that at C, we will need to use VC. It's equals to VOC plus ACT, right? And we know that this guy is 0, so we're looking for this, but we need an acceleration. So finding the acceleration has to be what you need to do. And most of the time, guys, it's given by the relationship between the bodies. So you have the first body, which is gear A. You have your second body, which is gear B. Then gear B has a pulley right here that is called D, and D is connected to C. With that in place, you can start realizing, per se, at this point where they meet, when A transfer power to A, they have the same tangential component of the acceleration. And you can relate that by saying that AT at A is the same one at 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 B, and therefore you can just go ahead and make an equation for this. Alpha A RA, it's equals to alpha V RB. You have this, and this, you can easily calculate RB. Then you have to know that B and D, they move together, so alpha B, it's equal to alpha D, right? And why is that important? When you go to the point where C connects with D, they both have the same tangential acceleration. So AC, it's equals to the tangential component of D. And the tangential component of D can be got by multiplying alpha D RD. With that, you will get the acceleration you're looking for. And once you have that with you, it's just simply plug and play and calculate your equations. So let's just start giving numbers to this whole thing. So like I said, ATA, it's equals to ATV, therefore alpha ARA, it's equals to alpha VRB. Okay? Okay, so this is 4.5 and multiply 75. You can put that in meters or millimeters. It doesn't matter because at the end they will cancel out. Radians per second square. So now that I have that, I can easily alpha v, it's equals to alpha v, and therefore I can calculate the tangential component right here. At, it's equals to alpha v times rd, where alpha d it's equals to 1.5 radians per second, and that multiplies d, which is 0.125. Okay, when I multiply that, I will get that this is equals to 0.1875 meters per second square. Okay, so now that I have the tangential component, I can easily plug those values into this equation as follow. So VC, it's equals to VO, or initial velocity, plus ACT. This one is 0 because it starts from 0, so VC will be equals to 0.1875. That multiplies the time, which is 3 seconds. I get the VC will be equals to 0.563 meters per second. All right, and now I just have to use, the position SC, it's equals to SOC plus BOC time plus 1/2 acceleration of CT squared. This is 0. This is also 0 because it comes from rest. SC will be equals to acceleration that was calculated, which is 0.18 times 3 to the square divided by 2, and I get 0.844 meters. That's how much it traveled. Okay. And with that, we just solved the exercise. The most important thing here is all the analysis that we had between the elements. When we have and we learn how to navigate that data, then we would be able to find what it's needed and what was asked. Okay, now we're going to talk about absolute motion analysis. In order for us to analyze the movement of these parts, we have a body that is moving in a rectilinear way, and then we also have another moving part, which is the window, and it's moving with an angular behavior. So once we have those two, we need to relate them both in order to find a successful equation that will relate, angular position and position as it is. And once we have that and we find the proper time derivative, the first and the second, we will be able to find, velocity and acceleration. What is a procedure, right? We're just using everything that we have learned until now. The velocity and acceleration of a point undergoing rectilinear motion can be related to the angular velocity and angular acceleration of a line contained within a body using the following procedure. We need to locate a fixed point of the body using a position coordinate S, which is measured from a fixed origin. Okay, once we have that, we need to start establishing a reference line that will be able to help us measure the angular position of that body. Using the dimensions of the body, we will be able to find an equation that relates the position and a function of the angular position. Once we get that, if we time derive, for the first time, in the second time, we will be able to find angular velocity and angular acceleration. So far, it's basically what we have done until now. And I wanted to explain that with an exercise. So we have right here this, I would say, this little motor that is making this move from here to here. And as it's moving, with that angular behavior, then this whole component T will be moving like this, back and forth, right? So what we need to do is to study an equation that will establish the movement of that one so we can start deriving in order to find what is needed. So link A and B is rotating clockwise, okay? As you can see here, at the instant theta equals 60 degrees, the slotted guide rod is moving to the left with an acceleration and velocity which are given right here. We need to find the angular velocity and angular acceleration of the link AB. That's all we need to do. So how do we do that? So now that we have that, we're going to study, I mean, this is just for a given interval time. So we need to find an equation that will work for anything. So we need to relate, like I said, position with angular position. So we have the engine, right, that is moving the rod from here, and this is given by theta. Well, we know that the displacement will be equals to theta then multiplied by the radius. Which radius? So it's given right here. This is 0.2. So displacement it's equals to, or position is equals to angular position that multiplies the radius. And the component of this 0.2 will be equals to 0.2 that multiplies cosine of the angle, right? That's what dictates the displacement, right? How it moved from that point to the other point. So if we derive that respect to the time, ds respect to the time, we will be able to find the time derivative, which in this case will be w, or angular velocity that multiplies 0.2, and the derivative of this will be minus sine theta. Okay, and if we want to go a little bit further than that, we can derive velocity respect to the time, and we will have to use these by parts. And if we do that by part, we will get minus 0.2 that multiplies cosine of theta, and this is multiplied by omega to the square minus 0.2 sine of theta, that is been multiplied by angular acceleration. So now that we have that, we can easily, because this guy right here, it's velocity, which is given here, and this guy right here, it's acceleration, which is given right here at theta equals 60. So when you have theta equals 60, you can just plug all these value into this equation and then into that equation in order to find omega and alpha. Now that I have the equations, when theta it's equals 60 and acceleration obviously negative because it's going to the left, minus 2 meters per second square, and velocity it's equals to minus 5 meters per second, then I can just easily use the equation. So the first one is minus 5, it's equals to 0.2 that multiplies minus sine of 60, and that it's multiplied by omega. If I solve for W, then I will get that W it's equals to 28.9 radians per second, right? And then if I use this into the second equation, I will get that minus 2, it's equals to minus 0.2 cosine of 60, and this has been multiplied by omega to the square minus 0.2 sine of 60, that is multiplied by alpha, or angular acceleration. So if I solve for angular acceleration, I will get that this is equals to minus 470 radians per second square, or you can also say that is 470 radians point second square going in the opposite direction. And that's it. That's basically what was asked of us. The most important thing with this, guys, is that we were able to establish an equation properly based on the geometry given, and that we were able to understood exactly what was asked of us. As this moved from one point to another, this whole component is moving into a rectilinear motion, and therefore we can use an equation that will relate them both. All right, and that will be it. Thank you very much for watching all my videos. I will see you in the next one.